ladies and gentlemen, this class recording has started. So, last week, we talked about the transition from one-dimensional motion into two-dimensional motion, right? Whereas one-dimensional motion, like these two examples right here, right, we're stuck on a straight line. Ball goes up, ball comes right back down, or with this one, the cart just rolls down the hill. Even though it's slanted, right, it's still a straight line because, okay, and then this, oh, I turned that off, there we go. Maybe. Come on, pen. There we go. Okay. But even here, while this cart is rolling down the hill, even though it's slanted, because of where the motion detector was put up, this is still a straight line. But in real life, that doesn't happen all the time, where things move just in one dimension. Sometimes we have things moving both horizontally and vertically. And we talk about those being projectiles, and the study of that motion in two dimensions being projectile motion. So, the key idea that we introduced on Friday was the idea that the horizontal motion does not affect the vertical motion. They occur simultaneously, but they are independent of one another, right? Yes, they're both happening, but one doesn't affect the other one. So anything that would happen to something vertically, like this red ball dropping, accelerated motion, the things keep getting farther and farther apart, right? We talked about that, influence of gravity, all that fun stuff. That's going to happen to the yellow ball as well, even though the yellow ball is moving horizontally while those things are happening. So they both contribute to the overall motion of an object, but they don't affect one another. And that can be a little confusing when we look at some other aspects. And on Friday, we looked at the video of this situation, right? That where if something is just dropped straight down or something thrown horizontally, they both hit the ground at the same time. Even though the yellow ball travels a much farther distance, but because the horizontal part doesn't affect what's happening vertically, that even though it's traveling horizontally, they will still both fall at the same rate and hit the ground at the same time because of the fact that the horizontal and vertical don't affect one another. Does that make sense? Good there? Okay, so to review those ideas, let's look at a couple of short videos. All right, so put this on here. I'm going to pause the recording because this is copyrighted material, so we'll be back in a second. All right, class recording's back on, everybody. Just so you know. All right, what I really wanted to do today was take a look at how these ideas of the separation between the horizontal and the vertical motion affect our quantitative analysis of projectile motion. How does it affect the actual numbers? How does it affect what we got numerically with analyzing where and when this object is in certain positions, okay? So on Friday, we very briefly got into this problem, which, if I remember correctly, is on page... Does anybody remember what page it was on? I wrote it down for you guys the other day, but I can't remember. 43? So this is on page 43 of your course companion, the paperback book. And it says here, okay, can you guys see? Do you want me to turn like a little bit of lights back on, or we don't have to turn all the lights back on?
I like those.
Okay. If you guys can see, I'm fine with that. All right. So it says an arrow is fired horizontally from the top of a tower 35 meters above the ground. The initial horizontal speed is 30 meters per second. Assume that air resistance is negligible. So, to start off, and I know for those of you that were here on Friday, we started this problem, but I'm just going to stake it all the way from the very, very beginning just to make sure that we follow it all the steps through. Okay, so if the beginning part sounds familiar, it's because we started this on Friday. Okay, first thing I'm going to do in this situation, and I made the picture a little smaller because I'm going to give myself a little more room to write here. First thing I want to do is make sure that we have a good representation of this situation, right? To make sure that we understand what we're looking at and how it all fits together. So, there's our ground.
Can it be me again?
Sure. All right. There's our tower. Right? There's Cindy standing on our tower.
Yeah. What's up, people? Isn't it purple pin?
Yeah, I changed it though, just because. Okay. So there's our bow, and what color do you want your arrow to be?
I want it to be that pastel pink.
It's not going to show up very well, but that's okay. All right. So there's the arrow. All right. Good. You have.
It's supposed to go. Gravity acts upon my ponytail.
That's like it's because it's like held up.
It doesn't
You know,
go like that.
so maybe it's really windy. No, it can't be windy because that would add resistance. So. All right. So it says here in the problem, right, that the arrow is fired horizontally. So it's set along this path. However, as soon as it leaves the bow, what starts acting on it? Gravity. So now it maintains that horizontal motion, but it also has a vertical motion that we have to deal with. And what's happening in the vertical dimension because of gravity? It's going to go down. What happens to its speed as it goes down? It accelerates, right, because of that acceleration of gravity, okay? So it doesn't end up following this path, right? It ends up following this path. And we talked about what shape is that going to make, as long as we can neglect air resistance. It's parabola, okay? And we talked about some other parabolic relationships earlier on, right? This is a parabolic relationship between horizontal displacement and vertical displacement, okay? So, are we okay with this situation right here, okay? Just to label a couple of things, right? It tells us that the tower is 35 meters off the ground. So this is going to be 35 meters, okay? And that the initial horizontal speed was 30 meters per second in this direction, but like we discussed, it never actually goes in that direction, right? As soon as it leaves the bow, it's going to start moving downward and eventually follow that parabolic path, okay? Good there. All right. So, first thing we're going to do is, let's go in order here, right? It says that calculate the time for which the arrow is in the air. I'm going to just make it a little smaller so I have some more room to work with here. Okay. All right, so I will do this whole problem here in blue. Okay. All right, the time for which the arrow is in the air. For those of you that were here on Friday, we discussed this a little bit, but just totally to review. The way that we need to go through these kind of problems, right? We have two motions going on at the same time, right? And that being the case, we talked about that we still use these 5 things to describe the motion of the object, right? The displacement, the initial velocity, the final velocity, the acceleration, and the time. We still use those terms and those concepts to describe the motion, but now we have to look at both the horizontal motion and the vertical motion separately because they occur simultaneously, but they don't affect one another. All right? Good with that? People that were here on Friday, does that sound, you know, so. All right, here, it's asking us to solve for the time. We said that time was unique in this chart because it's the only one that has to be the same both horizontally and vertically, because those motions are occurring simultaneously. So the amount of time that it's traveling horizontally is exactly the same as the amount of time that it travels vertically. If we go back to this picture here, I'm going to change something. I'm going to make this blue. That the amount of time that it travels horizontally on this trip is the same amount of time that it travels vertically on that trip. So when we're analyzing these two-dimensional problems quantitatively, we need to keep track of both our horizontal motion and our vertical motion, but time is the one thing that is the same for both of them. We may run into a situation where some of them end up being the same. That's a coincidental thing. Time has to be the same. All right? So, if we're looking for time, that means we can solve for either one of these spots in this table, and that will give us our answer. Okay? Now, we've identified what we're looking for. The next step in the process, what do we know? We said that there are two spots in this table that we can fill in every single problem right away, no matter what. And those two spots are here and here. Right? Our accelerations. We said that when something is moving in 2 dimensions, gravity is the only thing affecting it, but gravity only affects the vertical motion, right? So the acceleration vertically is going to be 9.81 meters per second squared. Usually that's going to be negative, because which way does gravity pull stuff? Down. So as long as we make downward our negative direction vertically, we can plug that negative sign in there. But we said that if we neglect air resistance, there is nothing to affect the horizontal motion. If there's nothing to affect the horizontal motion, what does it keep doing horizontally? Keep moving, but it's more importantly, it keeps moving how? Horizontally at a constant rate or constant speed, and that means that if we have a constant speed or a constant rate, there is no acceleration, because its horizontal velocity doesn't change. Good there? Those two things we can fill in right away. Now, it's a matter of going back into our information and getting what we need. So, we said that, it tells us in the problem, the initial horizontal speed is 30 meters per second. So we can plug that in here for the initial horizontal speed. These type of problems that we start off with are kind of special cases in that it tells us that the arrow is fired horizontally. If something is moving horizontally, what is it doing vertically? If it's moving horizontally, what has to be happening vertically? At least at the very, very beginning of this problem.
It's always going to be.
All right? If something moves horizontally, it's not doing anything vertically. Does that make sense? That being the case, in this situation where it says we fired it horizontally, our initial vertical velocity is 0. Now, does it stay that way? No. As soon as it leaves the bow, we said what starts happening to it vertically? Right? It starts going down, but more importantly, what starts happening to its speed vertically? It is accelerating. It is increasing in the vertical direction. But right now, it's not doing anything at the very, very beginning. Okay? Does that make sense? All right. Next. A tower 35 meters above the ground. That's where the arrow starts. Where does it end up eventually?
0.
On the ground, right? So if something starts 35 meters above the ground, but ends up at 0 on the ground, right? What can we use that to figure out? Displacement. Which displacement, Devin? Vertical displacement. What's our vertical displacement going to be? There we go. Our vertical displacement is going to be negative 35 meters, right? Because it starts up at the top and ends up at 0. Okay? Good there. That's all the information this problem gave us. First question it asked us to solve for was time, right? That being the case, right, if we're looking at Suvat to analyze the motion, we said in using a Suvat equation, how many pieces of information do we need to know? 3, right? So we can use then, because each one of them contains 4. right? So now, over here on the horizontal side, we only have 2 pieces of information that we know, right? On the vertical side, though, how many have we filled in? 3. So it probably makes more sense here to use a vertical equation, right? If you look back at your list of Subot equations, we need to find one that contains S, U, A, and T, right? So you can look at them real quick, or you can just wait for me to write it up on the board. Good there? All right. Now, on the test, we ran into a problem on this using this equation while we were solving for time, yes? Right? Because if you look at time in here, time shows up twice, but one time it's here, and one time it's squared, right? And that makes this a quadratic equation. But based on the information that we were given, what's the initial velocity in this problem? 0. So what happens to this term? That term just goes away, right? You multiply anything by 0, and then we end up with that 0, right? So we then end up with just like that, right? Plug it into your calculator, find out what it is. Did I do that right?
You don't substitute in the displacement?
Yeah.
Oh, you did? Oh.
Yeah.
That's
Is that what, anybody else get that? Yeah, okay. All right. So that's how long it's going to take for an object that we drop from 35 meters to hit the ground. But it's also how long it will take for this arrow, moving both horizontally and vertically, to hit the ground, right? Because the horizontal doesn't affect the vertical motion. Good there? So, in this table, we can fill in 2.67 for the time, but if we know the time in one dimension, we automatically know the time in the other dimension. Okay? Good there? All right, let's take a look at part B. So part B says the distance from the foot of the tower at which the arrow strikes the ground. I'm going to do this in blue, even though I said I was going to do the last one in blue, right? I didn't, because for a reason why. All right, so distance from the foot of the tower at which the arrow strikes the ground. If we go back to our original picture, right, that's going to be that distance right there, right? Going back to, what are we talking about here? What variable would represent that distance on the drawing? Displacement, which displacement though, Devin? Our horizontal displacement, right? So, I have the ability to do this, you don't, but you guys are working on the same problem. So here's what I'm going to do. I'm going to take all of these, yes, and okay. That table still applies to this problem, right? But now, part B is asking us to solve for that, right? Good there? Again, we can use a Suvat equation to analyze the motion, but now we just have to stick on the horizontal side, right? So, looking at the three things that we now have, because we can use the time from the previous problem, right? We're again going to end up using this equation, right? But now this one, solving this one becomes even easier, because what is our acceleration in the horizontal direction? 0, right? So what happened, because the only thing affecting the motion of this arrow is what? What's the only thing affecting the motion of the arrow? No. After we fire it, what's the only thing affecting its motion? Gravity. And gravity acts in which dimension? Horizontal. No, sorry. Vertical. Okay. So in the horizontal dimension, the acceleration is 0, so this whole term goes away. It becomes 0, right? Now it's just a matter of doing a little multiplication. Okay? So we should end up with somewhere around 80? 70 something? Oh, 80.1. You're ahead, yeah. Okay? And so that can go here. Alright? Good there. Alright. Now let's go to part C. Okay? So part C is asking us to find the velocity at which the arrow strikes the ground. Okay? Notice I changed colors again. Are we getting the color coding yet or no?
I don't have a color code.
That's okay. So, are you getting my color coding?
Yeah.
Okay? So, my color coding being, right? Horizontal stuff is in blue, vertical stuff is in red, but things that apply to both are purple, right? Because horizontal, like red and blue, like purple. Yeah. And what?
You colorblind?
Okay, well, that's fine. You don't have to. I mean, that's fine. It's just a visual thing, but whatever. Okay. It's good. All right. So this problem is asking us for the velocity at which the arrow strikes the ground. So here I am back at my picture. Okay. When it says at which the arrow strikes the ground, it's meaning the instant right before it hits the ground, not after it hits the ground. So don't say 0, because that's not the right answer. All right? Because after it hits the ground, gravity isn't the only thing affecting its motion anymore, right? Now there's like the ground and friction and all that stuff. But if we can stop this problem, or if this problem runs from here to here, right? The instant right after it leaves my bow till the instant right before it gets back to the ground, now gravity's the only thing. And that's what we really want to do, right? So yes, even though I made this as a circle, that circle is going to represent my arrow. All right? Right before it hits the ground, how is it moving?
Like downward.
Is it moving just downward?
And a little bit that way.
Okay, it's kind of moving slanted, right? Because it maintains this 30 meters per second velocity in the horizontal direction, but the entire time that it's been flying through the air, what has gravity been doing to it? Accelerating it which way? Vertically. So now it's still moving 30 meters per second horizontally, but it's also moving downward on the vertical dimension. Do we know how fast just yet? Well, that's the acceleration. Do we know its velocity? Now, that would be its horizontal, right? But vertically, what's been happening to it the whole time? It's accelerating, speeding up because gravity keeps pulling it downward and downward and downward, right? We don't know how fast it's going vertically just yet, but going back to this table, right, we can figure that out. That's another spot in the table that we can figure out with all the other information that we did, right? Does that make sense? Okay. Now, here's where this becomes a little bit tricky, okay? Let me get rid of all this. Okay. Here's a representation of this ball, or this arrow, as it's going, right? It's a ball in the picture, same thing with the arrow, right? The horizontal velocity, right, starts off as a certain value, and notice this arrow, the entire way down, continues to be exactly the same horizontally. Because the horizontal velocity never changes. It just keeps going forward, forward, forward at the same rate. But what's happening to our downward arrows? They keep getting longer and longer. I should make that one actually longer. There we go. Okay. Why? Because what's happening to its velocity in the vertical dimension? It keeps getting faster and faster. If we want to know how fast it's going at any particular moment in time, we can't look at just the horizontal velocity or just the vertical velocity. We have to look at the combination of both, right? And that's where we get into this idea of the vector sum, or the resultant vector. In the video, I kind of gave you guys this introduction, right? Something that's traveling northeast is actually traveling both north and east at the same time. The resultant velocity, or its actual velocity, is a combination of the north velocity and the east velocity. But it's not just as easy as adding them together. All right? Why? Because it just doesn't work that way. What we're going to start off with is looking at things that are at right angles to one another. Right? A north velocity and an east velocity are at right angles to one another. That means the combination of the two takes it in a northeasterly direction. But if this is 300 meters northeast, it's not 150 and 150, right? Now we bring in our trig identities to calculate how big those values are, right? So, going back to this picture here, right? Going back to part C, right? Here's our arrow, right? And when it gets to this point, it's traveling both horizontally and vertically. But if we want to know the velocity, we have to find the vector sum of those two. So what I'm going to do is take my red arrow and move it over just like this. Okay? Could you move it the other way? Yeah, you could. Okay? Then the actual velocity is the hypotenuse of that triangle that I just made. That's how we combine those two velocities that are in different dimensions from one another. Okay? Good there? All right. So let's go here. Okay? And I'm going to take this. I know. Or you could just use the same one. Wow. That is not what I want to do. See if this works. Whoa. Come on. Can I get this whole thing to move? Nope. Just the zero. Anyway. Okay. Can you guys see it even though it's like not top and low? Alright. So, these two arrows that we got here, when right before it hits the ground, are going to be the final velocities, right? So that means if we're going to calculate the actual final velocity or the resultant final velocity, we need to know this, and we need to know this. Okay? What's the final velocity going to be in the horizontal direction? 30. Why? Because what's the acceleration in the horizontal direction? 0. If there's no acceleration, what happens to the velocity? Stays the same, right? So this is going to be 30. And that means if we have this triangle, right? This side of the triangle is 30. Can we figure out the final velocity in the vertical dimension? Use another Subot equation, right? I would recommend this one. Okay? What's the initial velocity in the vertical direction? What's u on the red side? 0. So that just goes away. Alright? And then we can just multiply the acceleration times the time and get where we need to go. Right? Probably going to be somewhere about 25-ish or something like that. 26.2. Okay? Technically, it would come out with what sign? Negative, because which way is it going when it hits the ground vertically? Down. Right? Now, does that make a difference? Hold on one second. Let me finish this up real quick. What mathematical operation are you going to do here to find purple? So, not SOHCAHTOA. I would probably go with Pythagorean theorem, right?
Oh, just kidding.
Right? But when you square that negative 26.2, comes out positive, right? Check the calendar. There are several problems that are just like this one, right? Answers are posted there for you. Tomorrow we will change the picture just a little bit and make it a different kind of projectile, okay?